Hi there, this is Jacob Nash, and in this video, we'll be reviewing Unit 7 of AP Physics 1. So, let's start out with the equations that you need to know. Some of these are on your formula sheet, but not all of them. So, hang on, let me just mouse here. Okay. So, the equations that are red are the ones that you need to memorize. And luckily, the ones that you need to memorize are not that hard. At least they give you the ones that are longer, like those ones. So, we have, if you remember, you can relate this, which you might think that's angle, but that's actually angular distance or displacement. You can relate that to the linear displacement that we learned. You can relate this W symbol, which I know that's not what it is, but I don't care. I'll just call it W, to our V that we've used. And then this Greek A, which once again, don't care. That's not A, but it looks like the A. So those, remember to relate those. And you can see, how do you get from one to the other? You just divide the linear one by the radius to get the angular one. So you have to remember that for those. Also remember that 1 revolution equals 2 pi radians and is 360 degrees. If you know your unit circle, that should be easy to remember. And then these 3 equations are our rotational kinematic equations, and they are like the ones that we already learned. For some dumb reason, they only give you 2 of them, and that this one you have to remember, but it shouldn't be that hard. Just go to the linear one and then just replace all the symbols. But that's for some reason what it's like. Here's your torque equation. And I know that that's not how it is on the formula sheet. It's RF sine theta, but I think that it's easier to remember just FD, like where D is the radius. But it helps me because I think torque and then work. And so I just call torque Turk. Sometimes just think of it as Turk, because work is force times distance times cosine of angle, and Turk is force times distance times sine of angle. So if you remember Turk work, then that's what helps me. But you can also just know that that's the same thing, just in a different order, and there's an R instead of D, but they're the same thing. Then moment of inertia, you got to remember this one. I think it might be on the formula sheet, but I don't think it is, no, because well, we have m times r squared. This J thing is kind of just something I made up because that's not really a physics letter, so that I knew I could use it for something. But J, let's just say that's a fraction and it's different for the different objects, remember? Because in this video, I'm not necessarily going to review the content, just show you how to answer the questions and explain why. But 1/2, for example, that could be 1. Or we have 3/4, that could be 1. And something to remember, when things roll down an incline, if the moment of inertia equation has a J that is bigger, then it will take a longer time and we'll have a greater velocity at the bottom. Oh wait, never mind. It will have a smaller velocity at the bottom, because velocity at the bottom, which you shouldn't memorize this, but it's the square root of that times GH. Hang on a second. Just, you should derive that. Wait, just forget that. But anyways, what I'm just trying to say, that's what that J means. But that's what it's like. So anyways, that's something good to remember because the fraction will end up flipping over, and if you have a smaller velocity, you have a greater time. So that's just something good to know. So if an object had 3/4, it would have a less velocity than if it had 1/2 in that place. So then we have rotational kinetic energy, which is 1/2 times the I times W. So those are like the MV if you change that to linear things, and that makes sense. Then torque is I times angular acceleration. And that's kind of like F equals ma, force equals mass times acceleration. Then we have center of mass equation. That's not really used that much, but occasionally it is. And that's, you have a mass times a distance plus how many ever masses there are divided by all the sum of the masses. So, or really another way you could, but this one is one that's not on there. So the sum of the masses times their distance divided by the sum of the masses. That's basically what it is. Okay, then you have angular momentum, which equals I times angular velocity. And then the change in angular momentum is torque times time. And how you get to the linear momentum is multiplying, well, you multiply the linear by r to get to the angular. So that's different than the other things. And so MBR is the same thing as the angular acceleration, or sorry, angular momentum. What are the new variables that we learned? So we learned I, which was moment of inertia, and the unit for that is kgm squared. We learned Kr, which is rotational kinetic energy, which is in joules. We learned L, which is angular momentum, which is kgm squared divided by seconds. I know what the variables stand for, and you should too, but I'm just not saying it for time's sake. W, or omega, is angular velocity, which is radians per second. The Greek A, alpha, is the angular acceleration, which is radians per second squared. And then the tau, or the T looking thing, is torque, which is in Newton meters. And then the theta is the angular distance or displacement, which is in radians. And then L, well, we kind of already know what that is. That's the length. So now let's look at some questions where we use this. So we're trying to find the torque provided by force F. And remember the key thing to solving any physics problem, KFES. What you know, what you need to find, what equations you're going to use, and then solve it. So what do we know? Well, we know what is in the picture, so kind of skip that. We're trying to find the torque provided by force F to achieve rotational equilibrium. So, well, what do we now? We need to know the equations because we know what we're trying to find. What equation will we use to find torque? Torque is, I already said, force times distance times sine of angle. But we're not going to do that because all of these are perpendicular, which means 90 degrees, and sine of 90 is 1, so that means nothing. So that is what it is, or RF, if you look at the formula sheet. But how does that tell us how to find this one? Well, we know if we're trying to find a specific torque, we know that all the torques add up together to equal 0 in this case. So all the torques add up to equal 0. And how many torques do we have? It depends on how many forces we have. We have 1 force, we have 2 forces, and we have 3 forces. So let's call this one 3, this one 2, and this one 1. So it's going to be the sum of all the torques that there are. Might just be quicker to do this. Messier, but quicker. So here are the torques. And if we're trying to find number 3, then we have to get it by itself. So we subtract number 1 and 2. So negative torque 1 minus torque 2, because we subtracted them both on the other side. And by the way, this equals 0. That's why we can do that. And then that equals torque 3. I'll just put it, well, I already did that, so I'll just put it over here. So the torque number 1, that's going to be its force, which is 270 newtons. But we might need to make it negative because clockwise is negative and counterclockwise is positive. And if you don't know what those mean, think about a clock. The hand goes this way, so that is clockwise. And if it's counterclockwise, then it's when it goes this way. How do you know if the forces are clockwise or counterclockwise? Well, just look at where it's pointing and keep drawing a line that kind of curves over into a circle. Well, that's counterclockwise. So that this thing's going to be positive. And then this one, if you continue it down and make a circle, that is going to be negative because that's clockwise. And same thing with this one, that's negative. So this has to have a negative force, or not necessarily the force, but the torque will be negative. So number 1, we have 270 for the force. 270 for the force. And what's the distance? The distance is 12, from the pivot point, by the way. So that's why I don't really like RF, because it's not always a radius, it's distance this time. So that's 12 meters, and it's in meters, so that's good. And then once again, okay, so that's torque 1, and then for torque 2, we have to make it negative again. So the negatives will become positive. This is 1080 newtons. And then you multiply that by the distance, which is 24. So that will give us our torque 3. And it should be positive. And if you type that in the calculator, it is positive, and it is 29,160 Newton meters. Make sure you know your units. Touch screen on my computer doesn't work very well. So that is the answer for that one. Now we're saying, what is the magnitude of force? Okay, what do we know? What we're given in the picture. What are we trying to find? Force. How do we find force? What equation do we use? Well, if we know torque and we know distance, then we can use the equation that we already used. And solving for F, this is what it is. And you do the torque, which we just found to be 29,160. The distance for F is 48 meters, giving us a force of 607.5 newtons. All right. All right. We have Gina that rolls a bowling ball with a mass of 7 grams. Write that down right now. It's always what's good to do. 7 grams. Oh, that's so stupid because it's 9 kilograms. So convert that, and that is 0.007 kg. They do that sometimes. You gotta make sure you use the right units. Always kilograms, always meters. But how do you do that? How do you change from units? In case you didn't know, well, if you look on the back of your formula sheet, it says grams is the base unit, and then kilograms, it's saying is 10 to the third. Wait, right? 1, 2, 3. Yeah, 10 to the third. So if you're trying, this is what it's like. So 7, and it is grams. And when you're doing a unit conversion, it's saying that 1 gram other way around. It's saying 10 to the third grams is equal to 1 kilogram. That's what it's saying. So you have to solve that, and that actually means you're doing 10 to the negative third, which gives you that. Or you could just know to move the decimal to the left 3. But always know if it's in grams, the kilogram should be smaller. That's always what it's like. So anyways, erase this. Oh, never mind. Because I already drew white over this to not show the answers. Okay. Don't know why it's gray. Okay, so now we know that we also know that the radius is, we would convert that to meters and say that it's that. And it has a velocity of 6 meters per second. So it's saying, what is the rotational kinetic energy? What is rotational kinetic energy? That's what we're trying to find. So we figure out what equation to use, and it is 1/2 times moment of inertia times velocity, angular velocity squared. Don't forget the 1/2. Then you do, I don't know what the moment of inertia is. So you have to do an equation within an equation, and that tells you which one to use. So we do 2/5 times, what was the mass? It was 0.007, and you multiply that by the radius, which is 0.109, and you have to make that squared, and then so that's the I, and then for the angular velocity, that was, oh wait, they didn't tell us. So you have to do another equation within equation. And we know that angular velocity is linear velocity divided by radius. So we'll have to do 6 over, takes so long to write on this thing, sorry. I'm trying to write with the mouse, and writing on the screen doesn't really work. And that has to be squared too. So when you plug that in, you get 0.05 joules. That's the answer. Now we have to know total kinetic energy. What do we know? What they already told us. What are we trying to find? Total kinetic energy. And what is the equation for total kinetic energy? Well, it just means both kinetic energies combined, which is rotational kinetic energy plus linear kinetic energy. We already know what rotational kinetic energy is. That's what we just found. And it is 0.05 joules. Now we just have to find linear kinetic energy, which is 1/2 NV squared. And you do 1/2 m, what was our mass? 0.007 times velocity squared. And when you do that, you get Okay, gotta have calculator. Let me look at my calculator. Yeah, 0.007 squared times 36 plus 0.05 is, the answer is, wow, that does not seem right. Well, hang on, let me look at my calculator on the computer instead. 0.05 and plus, 1/2. So 0.007 squared. It did 2. Dang it. These online calculators are so dumb. Okay. Squared plus or times 0.5 times 36 plus 0.05 equals, well, what do you know? 0.05. I don't know if I did the calculator did the wrong thing. I guess maybe we just had very small linear kinetic energy. If that was the case, I still did the right process. I don't feel like getting up my TI-84 right now. So that's how you do that one. And we're gonna just skip this one for now because this video would be too long. All right, let's look at a more kind of question that is actually what thing you would see because on the exam, because we don't usually get the ones where you just happen to be able to you just use an equation and find a numerical answer. But so we still use the same process. A rod is initially at rest. Okay, that might be important. Then there's 3 forces on it. It is 0.5 meters from the pivot, or that it's saying basically the pivot is 0.5 meters on each end. Like it's just basically in the middle, and the length is 0.5 for both. So that's going to be the same. And if friction between the rod and table prevent it from rotating, what is the magnitude of the torque exerted? So basically, what are we trying to find? Torque. What equations can we use for torque? Torque is force times distance, as we already looked at. And it's sine of angle, but these are all perpendicular, so don't need to do that. Then we need to know the specific torque for the specific torque for friction. So we have a torque right here that is, we have a force right here that is 20 newtons. And I'm not going to explain this again, but that would be negative because that's clockwise. This is nothing because, or actually, yeah, we can still use the sine of the angle because this is not perpendicular. Sorry, didn't mean to say that. This is an angle of 0 with the rod. See, like what I'm talking about right here, this is 90-degree angle with the rod. Right here, 90-degree angle. This is a 0-degree angle. Sine of 0 is 0, so there is no torque right there. And then this one has positive torque because it's counterclockwise. So we can do the sum of the torques, and torque 1, let's just call this 1, let's call this 2, call this 3, and let's call the frictional torque just TF, which is what we're trying to find, TF. So the first torque we do, it is negative, so we do negative, and then the force is 20, the distance is 0.5, The angle is 90, sine of 90 is 1, so we don't have to put that. Plus, the torque of 2 is 0, I already said why. Then torque of 3 is positive. We have 20 as the force, and then 0.5 as the distance. And then we have plus this torque that is frictional that we're trying to find. And if we rearrange that, then we get, we would get this, we would add this one to the other side and subtract the other one, so it would still be the same thing basically, just because these are just opposite signs, but they would just switch signs. You put it on the other side. So basically this one, when you put it on the other side, is positive, and then you would change it to 10, and then minus 10. Wait. Oh, I'm sorry. I messed up something. This is not, this is counterclockwise. Or sorry, this is clockwise, so it is negative. Got mixed up, sorry. So that would mean this is negative also. And when you put it on the other side, both are positive. So it would be 10 plus 10 equals this. And so that means the frictional torque is 20. Took long enough. All right, now let's look at this one. This one doesn't have any numbers, and we just got to think about what it is. A rod is initially at rest. It is connected to a pivot that allows it to rotate. A lump of clay is thrown to it, and a lump of clay does not stick to the rod. The lump of clay eventually goes to rest. In figure 2, what linear collision is analogous to the rotational collision? That just means it's like, oh, it's like that, you know? It's like, oh, just like how if it was linear, it'd be like this. It's like this. That's what it means. So what are we trying to, well, the KFES doesn't necessarily work in this situation because there's not really, I mean, still we're going to use equations, but you don't really even have to for this one. So let's look at what happens in figure 1. So the lump of clay is thrown. This thing is at rest. It does not have a linear velocity or a rotational velocity. This thing does, though, this lump of clay. But then this thing rotates after it hits it, but this thing goes back and then it's at rest. So let's see which one of these answer choices sounds like that. A block is in the positive direction and comes into contact with it collides with the second block that is in the negative direction. There is not two things that are moving. This thing's saying one thing is in the positive direction, the other is moving in the negative direction. Only one thing is moving in our situation, so that's not true. All right, then what about B? A block is traveling in the positive direction and it collides with another thing at rest. After the collision, they move together. No, it doesn't stick to it, so that's not right. A block is moving in the positive direction. Oh, just like A, that's not true. A block is moving in, and why that's not true is because that. After the collision, the first block goes to rest. The second block goes in a direction that the first block originally traveled. That is what happens. So that's the answer. All right, let's look at this one. This is a graph question. Oh, sorry about that. This is not the right thing. A. Okay, so a block of mass m, object of mass m, is on a pulley. The pulley has a mass of 0.5 m. Oh, well, okay. They'll be stupid like that. They won't tell you kilograms. Fine. Okay, the object is released and it falls to the floor. That's something important because You'll see why in a minute. Which of the following pairs of graphs shows the angular speed and the vertical speed? So and it's talking about of the falling object, or of the falling object and the falling object and it's cut off. That's weird. But it's for the falling object and the pulley. So let's look at what happens here. So a little bit glitchy, but let's think about what happens. So it's on there, but then it's going down, and then just imagine it, it just falls off of the pulley completely and it goes on the floor. So let's just start with the block. The block, vertical speed of the object, angular speed of the pulley, sorry. That's for the pulley. That's for the block. Okay. For the block has a vertical speed. Let's think about it. It's like it's going down, dead ground. Not dead, but whatever. So we know that its speed is going to be 0 at the bottom. So CD, bye-bye. So what about, is it A or B? Well, so we know that that's what it's going to be like for the object. What about for the pulley? The pulley is, it's moving. But when the block falls off of it, that doesn't make it stop moving. It keeps going. And then it's like, so it's A, because it doesn't stop moving. That's why it's important to know that it falls, because if it didn't fall off, then it would make the pulley stop too. But since the block falls off completely of the pulley, then the pulley keeps spinning, and it's like, So there you go. That's what it is. All right. Sketch the angular displacement graph for this. Well, kind of just forget that. That's because I took this from something that already had other parts. So it's basically saying take this and make instead an angular displacement graph. So if it's versus time. So we have time in seconds still. But instead we have angular velocity, instead we have angular displacement, which is radians. And let's just make this, and I know it's RED, but I just don't feel like writing it. So 10 or 20, 10, and then 0. And then just real quick. 1, 2, 3, 4. Done. All right. So, well, why don't we do the area under the curve so that we can find out because we know area under the curve for a velocity graph is the distance, even when it's rotational. So let's look at this. Let's split it up into a triangle and a square. Okay, so we're doing that. All right, let's see for the triangle. 1/2 the base. The base is 10, or sorry, the base is 2. So 1/2 of that is 1 times the height. That is 20. So 1 times 20 is 20. And then for this thing, base times height, base 2, or length times width, whatever. Base 2, height 20. That means it's 40. So the total is 60. That's not what they're asking for, but that's just something to know. But basically, if it has, it's it's going to start at position 0, so right here. And at 2 seconds, there's 20 radians. So let's do this. And, oh, sorry, that's not the correct way to draw this graph because it goes past 20. So we have 40. No, just know that you have to have your axis title. I'm not writing that right now. Okay, so at 4 seconds, you have to do 40, or it's at 40. So you might just say, okay, no, it's not going to be a straight line. And here's why. Here's a hint to know. Whenever there is a, sorry, this thing froze. Whenever there is a straight line like this that is like that has a slope for velocity, it's always going to be like a exponential thing for displacement. And whenever we have a flat velocity, then it's going to be like this for displacement. And whenever we have 0 velocity, displacement is going to be just flat too. That's what it's like. So we know for the first part, it's going to have to be exponential, but for the second part, then it's going to be straight. That's what it's like. So hopefully that makes sense, because this for velocity, this for displacement. This for velocity, and it's not 0, then it's this for displacement. 0 velocity, this displacement. All right, that's that one. All right, and then the last question that we're going to look at is this. It's saying there a graph shows the torque as a function of time. Okay, so this is torque, this is time. What is the change in angular momentum after 100 milliseconds? So what do we know? Oh, just look at the graph. That's what we know. What are we trying to find? Change in angular momentum. What equation can we use? Well, we know that it is torque times time. Oh, good. That's what's on the graph. So let's see. Torque times time. Do we need to do the slope? No, because that would be torque divided by time. Y over x. So we have to do area under the curve. There we go. So area under the curve is what we're trying to do. And don't get tricked that if it says after 100 second or milliseconds, you might be like, oh, okay, that means 0 because the torque is gone. No, you think that the momentum just goes away? No, the torque does after that. So don't get tricked by that. You would have to have something under the axis like this to exit out, but that's not what it's like. So don't get tricked by that. So let's split this up into triangle and here and a triangle here. But if you notice, there's something stupid about this question. What is it? Milliseconds. Oh, thank you, College Board. Thank you. How do you convert from milliseconds to seconds? Well, you have to divide by 1,000. And they simply could have just done that, said 0.5 seconds, 1 second, but they just had to be stupid and not do that. So know that that's what that is. So let's just kind of forget about these things and just know that that's what it actually is. So triangle, area of a triangle, BH divided by 2. B, 400, H, 6. 400 times 6 divided by 2. Oh, sorry, not 400, 0.4. 0.4 times 6 divided by 2, 1.2. I'll just write it above here because it's kind of messy down there. And then what about this one? Base, 0.6. Height, 6 divided by 2, 0.5. No, not 0.5. Why is that not on there? 6 times 0.6 divided by 2. 6 times 0.6 divided by 2, 1.8. And you add those two things together to get 3 kilograms meters squared per second. Good. So that is the end of the Unit 7 review. Remember, just as a sort of like recap, do this so I can write down that. As a recap, as a recap, there are certain equations you have to remember, and that is at the top. So I would take a screenshot of this or something, and luckily they're not that hard to remember. And what you can do, let me get back to this. What you can do is, if you have the linear thing, if you divide it by the radius, you get the angular thing. And this works for these in relation to these. Okay. Then you need to remember torque equals force times distance times sine of the angle. You need to remember angular momentum equals moment of inertia times angular velocity, and change in angular momentum is torque times time. Also remember that rotational kinetic energy is 1/2 times IW squared. And also remember, what am I forgetting? I know I'm forgetting something. Oh, also remember torque equals this. And if you can remember those things and use them correctly using KFES, you should get your questions right. Because a lot of the mistakes that we make is just because you don't understand what they're asking or what you need to do. But you will think of it as long as you know your equations on the formula sheet and memorize ones you need to memorize. You write down what they tell you, you write down what you need to find, and you look at what equations have that thing. So if they're saying find torque, look at what the heck equations have torque in it, and then figure out which one has other things that they already told you about. Then use that equation to solve and get the answer right. And remember to convert to the other units because they do that sometimes. So that's it for this video. Thanks for watching, and I'll see you in the next one.